there's still no good or convincing answer really that we can give to people who ask what is the spatial resolution of EEG and MEG. So I'm really going back to the roots, to my roots and to the basics of the problem here. Sometimes I think people seem to think if something is so simple that I can understand it, then it can't be useful or interesting, because the brain is complicated, so our methods should be complicated, but I'm really trying to keep things simple here, as simple as I can. And I'm trying to show that these simple concepts, I think, can really be useful for the application of EEG, MEG source estimation. Okay, let's start at the beginning. So this is just an illustration of why we call the EEG, MEG inverse problem a problem. So we measure EEG and MEG signals around the head or on the scalp, but we are interested in what's going on inside the head. So we somehow have to invert our data, our model. So this is a little bit more detail on that. So our data are produced by some sources in the head, and there's a linear relationship between the signals we measure with some mixing in the middle between the data that we measure and the sources, or the unknown source strength are in a vector J. And all this can be expressed like a nice equation. And we can also solve this equation in principle in a linear way and say, okay, we want to multiply our data with some inverse matrix to get our unknown source strength in the head. So now the holy grail is to find this kind of inverse inversion matrix that gives an accurate solution for the inverse problem. There are also nonlinear problems, but nonlinear solutions, but I'm focusing on the linear ones here. And here it's illustrated that we have 3 unknowns, but only 2 data points. In reality, maybe we have 300 data points and 10,000 unknowns. But this inverse problem is not unique, so we have to impose certain constraints. We don't have 100% accurate spatial resolution here. So what do people usually do? Well, one thing you often read is you simply pick the one solution among the infinitely many that minimizes the norm, so minimal source power across all the sources. However, to cut a long story short, this is more the result of mathematical desperation rather than really physiological or cognitive or whatever constraint. So somehow you have to get a unique solution. Here is one. Similarly, you can use Bayesian approaches. Of course, they are more principled in a way. You get the most likely solution. However, is most likely really what you want to know, because you still don't know how reliable certain features are in your solution. What you want to know is, are the peaks that you see in your solution reliable? Is there a source where you see a peak or not? There are these ideas of ghost sources, and spatial resolution is limited. So you still don't necessarily have the information that you need in this experiment as an experimenter to interpret your solution. And I would really like to suggest, the best way, I think, to think about EEG, MEG source estimation is via the blurry image analogy. Think about looking at the brain, that is sort of what you see behind the screen through a slightly blurred windscreen. So I actually think that's pretty accurate because, things that are closer to you can be identified reasonably well. Nothing is completely clear, but with some prior knowledge, you can make out that there's a car there. Things that are further away are obviously more blurry, so you can resolve fewer details. There might even be some artifacts, some stripes here that are not representing any particular, object, but some leakage from other objects and some artifactual light coming in. So I actually think this is a good way of thinking about the inverse problem in EEG, MEG source distributions. Okay, this is not completely new concept. So imagine you're doing astronomy or microscopy. You have an image, you look through a lens. You want to know, how much does the lens blur the image, the true image under your microscope or telescope. And if you see something like that, then it's bad. So a point source, something that you think is a point source, is blurred around. So you have a point spread function here. That's how they call it. That actually blurs the point object into a large area here. So that's not so good. But if you know these point spread functions for all your point objects, in this case stars, then at least you can make some predictions of what stars you can separate from each other and which you can't. And this is sort of the kind of problem we have with our dipole sources in the brain. This, by the way, is the picture, from the Hubble telescope when it was broken. So they then fixed it and they got the point spread function right. And in a more abstract way, this is what we want to know. If there are point sources somewhere, like in one location here, and we know that our source distribution is not a point source, it's somehow distributed, then we want to know how far away can 2 sources be to be separated, or how close can sources be before they become blurred into each other. So that defines or describes the concept of spatial resolution. That shouldn't really be very surprising. So to do that a bit more formally, but there's really just one slide to highlight this concept, there is something like the resolution matrix that tells you actually the relationship between your estimated source and the true sources. And that's a good thing to know. So unfortunately, we can't invert that. So we can't estimate a source and then get the true source from it. I mean, that would be too simple. But at least we now know what kind of windscreen we are looking at. So this is the windscreen that tells us how we are looking. The estimate is what we actually see. The true source is what we would like to see. And R is basically in between the two. So R is basically the windscreen that tells us how blurred the image really is. And by the way, if you want to get the optimal R, so at least we can optimize that and get the best possible one in the least square sense, then you actually get the L2 minimum norm estimator, which for me is a good reason actually to pick that method unless you have any other a priori knowledge. And this resolution matrix gives you two concepts that are related but still independent and quite important. Importantly so. So there's the crosstalk function, the point spread function. A crosstalk function tells you for one particular location that you're interested in. So if you just want the time course, for example, for this one particular source there in depth, how much do other sources leak into that estimate? So sources that you might not be interested in, but they might still be active. And the point spread function tells you, well, imagine there is only one source there, so one point source. How much does it actually spread out into the neighboring areas? So these are two different concepts, but not completely unrelated either. And if you know those for all the sources in your brain, because they superimpose linearly, you can make predictions about what source you can separate from each other and which sources might be too close to each other to actually be separated. Okay, let's look at a few of those. So that's the nice thing. You can actually plot them. So if you have some regions of interest, in this case, occipital pole here, you have a very nice point spread function. In this case, I should say this is minimum norm, EEG and MEG together. And for minimum norm, you actually have point spread functions and crosstalk functions in one image. So the same distribution visualizes both of them. So very nice spatial resolution in the tip of the occipital pole. I would say great, good spatial resolution somewhere along the motor strip. But as soon as you go somewhere in depth, it's the great, the good, and the ugly here. So for deep sources, you have, you can say two things. First of all, if there is activity there, it will spread into the anterior temporal lobes. Or if you are only interested in that source and you design a spatial filter for only that source, it will be mostly affected by sources from the temporal lobe. So these are the two interpretations, crosstalk and point spread for this source. Okay, so you can, of course, not really conveniently look at 10,000 of those, across the whole cortex. So you want a way of summarizing features of spatial resolution and maybe analyze them in a more systematic way. So that's why we can define rather simple resolution metrics, which I think are actually the things that experimenters need to know, when they look at these kind of data. So imagine you have your little point source somewhere in one voxel or vertex, and you get a point spread function, in this case one-dimensional, so along space like this, or the peak might be somewhere else, so you want the localization error, and then it has a certain spatial extent, so you want something like the spatial deviation, basically the standard deviation in space. And you may also want to know across different point spread function, crosstalk functions, how the amplitudes differ. So if one is much, much higher than another one. So these are already three measures that you can define that are rather intuitive and quantitative at the same time. So we computed them for a range of methods for the Wakeman-Hansen data set. So we looked at 5 methods, so the classical L2 minimum norm solution, and then the depth-weighted version and 2 noise-normalized versions, and at a kind of beamformer, which I'm going to call dipole filter in the following because of some choices I made, but I would say it's sort of a maximum likelihood beamformer. It's a very special kind of beamformer. And we looked at 3 resolution metrics: peak localization error, the spatial extent, and relative amplitude. So let's start with a question that many of you are probably going to ask themselves, before they run an MEG study: should I get my hands dirty and also add EEG electrodes? If you only look at peak localization error, like many people do, so they only look whether the peaks are in the right spot, then you will see, so we now computed point spread and crosstalk function across the whole cortex, and for every location we compute a peak localization error and we plot that as a distribution. And you can see it's up to 5 or more centimeters as soon as you go into the depth of the Sylvian fissure here, for example. This is EEG and MEG combined. This is MEG only, and this is the subtraction. You can actually see not much is happening if we combine EEG and MEG together. The difference is close to 0. But if you actually look at the spatial deviations or the spatial extent of our point spread and crosstalk functions, you can clearly see that values are lower for the EEG and MEG combination. Also in the difference, it means that the values for EEG and MEG are lower, so you can gain a few centimeters here on this scale. And if you look at overall amplitude, it's not that conclusive, but in general, red colors here mean that EEG and MEG are actually better. So the ideal distribution here would be 1 everywhere. So in this case, higher values, positive values mean EEG and MEG is actually closer to that ideal. So that means EEG and MEG are clearly good in order to clearly improve spatial resolution if you look at the spatial extent of point spread and crosstalk function, and that's particularly relevant if you have multiple sources that you need to separate from each other. So peak localization error in this case is not everything. If we now look at different methods, so this is quite a complicated slide, but here we look at the point spread functions first, and this is the localization error for every method individually, plotted just as a distribution as before, and these are the subtractions L2 MNE minus whatever is in this column. So here in this case, peak localization error is clearly highest for the L2 MNE. So red colors here in the subtraction means that L2 MNE is the loser, maybe some advantages to DSPM, but clearly other methods, as promised, if you read the literature, improve localization error. However, this is for point spread functions only. As soon as you look at crosstalk functions, they are actually all the same. And that is quite clear if I would show you the formulas. So all these methods actually only improve point spread, but they actually don't improve the crosstalk. That means, it improves the localization property. So if you put a source somewhere and you look how it spreads, that changes. But as soon as you're interested in one particular source and how other sources spread into that activity estimate, actually nothing changes. Might sound surprising, but with a bit more time, I could show you why this is the case. The beamformer is a bit different here. But in this case, the differences are quite small. If we look at spatial extent, again for the point spread functions here, we actually this time we do see differences, and in this case the colors here in the subtraction are mostly blue. That means as soon as you take the spatial deviation into account, your methods get worse if they differ from L2 MNE. So you may have gained some localization error, but you are losing spatial resolution in the sense of the width of these point spread functions. Again, the crosstalk functions actually don't change at all for the minimum norm-based methods, and the beamformer, the dipole filter in this case, does change quite a lot, and actually quite a lot to the worse. It's much worse on this measure than minimum norm because it's actually a dipole filter. It doesn't really care about distributed sources. Again, the details I can't really tell you here. And then there is the relative amplitude measure, which is a little bit more difficult to explain. I will just highlight this here. So for point spread functions, it's a bit inconclusive. So you gain some and you lose some if you compare L2 MNE with the other methods. I would say for the crosstalk functions, usually higher values are better in this case. So red means that L2 MNE wins. And this is at least the case for these two methods. Again, for other methods, you seem to gain some amplitude estimation accuracy here in deeper areas. So it's a bit of, win some, lose some here. Okay, so this was just an overview of what I think people could all do with their own measurement configurations. I mean, this will vary a lot depending on whether you use EEG, MEG combinations, how many sensors, which MEG system. But the nice thing is that these things are really quite easy to compute. So hopefully different software packages will offer these things in the future. I'm a bit surprised that they don't right now because it's really simple to do and really useful. But for some reason they compete more on the number of methods they are giving you to analyze your data rather than actually tools to evaluate your source estimation results. And applications for which this is potentially relevant, and I really just have 2 more slides on this. So one thing that Resvan Faraj did here at the CBU, she used sort of resolution measures to optimize parcellations of the cortical surface. So obviously, I mean, with limited spatial resolution, you don't necessarily want to compute connectivity matrices, 10,000 by 10,000 vertices, because they are not all independent. You might want to downsample, but you don't want to undersample either. So this depends on the spatial resolution of your measurement configuration. And she found a way of using resolution measures based on crosstalk functions that find an optimal parcellation, or an adaptive parcellation for different EEG MEG setups. And finally, you might not be happy with what you see. Some crosstalk functions might not look the way you may want it to look, and you have additional constraints. You may want to suppress crosstalk from certain sources completely. Some regions of interest while still suppressing other sources and noise. So the linear framework offers you all these possibilities in relatively simple ways. So this is something that we've done in this paper. And so finally, to conclude, yes, half a minute, I've still got left. So first of all, I think the linear toolkits really offers you a lot of really simple and comprehensible and useful tools to actually look at your methods in an assumption-free way. By that mean you don't have to justify a certain norm or a certain equation. So it really tells you, what kind of blurry lens you're looking through into your brain. So you need you need both point spread and crosstalk in order to evaluate the spatial resolution of source estimation. You should at least cover localization error and spatial extent. So you can't just look at peak localization alone. So it might lead you to the wrong conclusions. And our methods comparison demonstrates, there is no best method. You can always only make trade-offs between different resolution criteria, which you have to justify yourself for the method task at hand. And one thing I would like to highlight, point spread can be cheated. So you can get reasonable point spread for sources in deeper brain areas. However, if you look at the crosstalk analysis, you will see that you can't really cheat. So you can't really get crosstalk that is not affected by sources close to the sensors more than by deeper sources. So for me, that actually means that deep sources will remain problematic for any source estimation method. And finally, the linear methods already provide quite a comprehensive toolkit to create adaptive source-based parcellations and to also design spatial filters more flexibly if you have specific assumptions and more specific applications. Okay, and with that, thank you very much to everybody who has contributed at some stage, and the MNE Python guys for their patience with me when I tried to hack this into their code. Thank you very much.